Stretching nearly 800 meters, the NPV Argonne is a fusion-powered nuclear pulse spacecraft. The first of its kind, this vessel represents a generational leap for nuclear propulsion. The spindle-like 215,000-ton Argonne has a specific justification to its creation. It will provide long-haul missions from lunar orbit to the gas giants. When in orbit around Jupiter, she will harvest resources from its atmosphere without reliance on local facilities. With a predicted annual payload throughput of 500,000 tons, the Argonne will provide the growing industrial base residing among the inner orbits with hydrogen, helium, and other useful chemicals. Conversely, she will transport raw aluminum and iron from Luna to the outer planets for use in construction projects. She will house at most 800 souls against the solar tides and bear the responsibility of directing the combined human efforts of exploring space. The NPV Argonne will become the new command center of space programs beyond Earth, and unlike on Earth, the command and control responsibilities here are shared by a central scientific and civilian leadership, a group of individuals who lead the effort of human exploration from the same point in time and space. Work being done in nuclear technology today indicates an identifiable vehicle design which will surpass the legacy Orion concept scope and allow the range and fuel efficiency of nuclear pulse propulsion to be enhanced. Humans have already pursued the necessary aspects of directing fusion plasma using magnetic, electrostatic, and inertial methods. The technical problems arising from containing fusion plasma are significantly more complex than sustaining a fission reaction, but there are commonalities between both techniques. While more difficult to produce and sustain than fission, when a fusion reaction occurs, it can be likened to a high-temperature fission reaction for the sake of comparison. Nuclear pulses offer solutions to the thermal, material, and dynamic limitations of traditional rockets, but pulsed reactions also mediate the problems of shaping nuclear plasma, since small detonated devices can utilize the directional nature of a sustained nuclear reaction to influence vehicle motion. Nuclear detonations can be asymmetrical in nature, as influenced by the material composition and design of the fusion or fission materials. We already know that self-actuated thermonuclear devices are directional in nature, so the same applications are viable to externally detonated devices so long as considerations are made to the device design. Future developments of NPP will hinge on designing these small fusion devices, known as microfusion pellets. In contrast to the nuclear devices of Orion, microfusion pellets contribute far less to the vehicle mass since they can be smaller and lighter while providing equal thrust. The pellets can be simplified into three parts: an enclosure made of gold alloy, a frozen deuterium and tritium fuel crystal, and a lensing cavity filled with hydrogen. The frozen deuterium-tritium fuel crystal is heated and compressed by laser energy. This eventually causes a fusion reaction. The hydrogen stored in the device's lens reaches momentary pressures in excess of 100 gigapascals, creating a partial transition into the first phase of solid hydrogen, where the molecules are allowed to freely rotate within a dense array. This phase allows the hydrogen lens to quickly absorb the thermal load of the ignition laser, which allows further solidification as the hydrogen reaches phase 4. In this phase, the excited molecules are stacked in alternating sheets of loose and strongly bonded structures, which permits the fusion cascade to quickly make use of the hydrogen as fuel. While the lensing cavity contributes little to the overall total power output of the fusion pellet, it provides a directional component for the fusion processes to follow and permits the asymmetrical detonations we expect from nuclear propulsion pulses. We might also use moderator materials which would contribute to the detonation's asymmetry. Pulsed nuclear fusion will permit directional fusion detonations without the expensive and complex containment systems typically associated with shaping nuclear fusion. The main advantage of pure fusion over thermonuclear devices is fuel efficiency and a low level of industrial development needed to build laser fusion-powered vehicles, but this comes at a significant energy cost. An apparent obstacle in pursuing pure fusion nuclear pulse propulsion will be these systems' high energy requirements. As opposed to Orion NPP, microfusion pellets will not self-detonate with the assistance of a fission tamper, so the initial energies needed to achieve fusion must be provided from an external source. Realistic fusion systems look to lasers for initiating fusion. Lasers appropriate for application include continuous wave lasers, pulsed and ultra-fast lasers. While triggering nuclear devices can be done with normal continuous wave lasers, pulsed lasers can pump more energy into a small object over a short period of time. This mode of operation is preferred since detonations occur over intervals of a second or longer, so the lasers only draw power for a small fraction of the total propulsion impulse. Pulsed lasers have other advantages as well. They can be chirped, allowing a sweep through a specific range of light wavelengths, amplifying the pulse beyond its original peak intensity. There is also the phenomenon of optical parametric generation, where two or more lasers can be tuned to different frequencies and focused on a mixing medium like a crystal. This process allows us to combine the sum energy of two different photons into a third photon generated by the interaction. Optical parametric generation allows energies potentially absorbed by the pulse device to be multiplied without additional focusing or complex solid-state controls such as those used in chirping. All of these techniques, chirping, optical parametric generation, and laser design, work together to reduce the total energy needed to operate the laser array. This area is where laser-triggered fusion begins to show real advantages over pusher plate designs like Orion. They can accomplish the same high performance with a fraction of the fuel mass, and fuel mass is cheaper to produce. The environment of space means any energy pumped into the fusion device via laser will be largely insulated, and thermal criticality of the fuel mass can be achieved with a minimal waste of energy. Our hypothetical Argonne interplanetary tug has opted for an array of 45 laser amplifiers. Each amplifier utilizes plasma electrode Pockels cells, which are extremely fast prismatic gates, as well as optical lenses and filters to increase an initial laser pulse of about 0.001 joules into an intense laser emission of over 200 million joules, focused on the microfusion pellet and lasting a few trillionths of a second. As the Argonne initiates a thrust maneuver, it deploys a single 15 kg pulse device from within the concave face of its pusher umbrella. A brief intersection with the laser array's focal point will allow the pulse devices to be struck by picosecond laser impulses over a brief interval of a few milliseconds. In our design, the pusher plate is an integral part of the vehicle's mission as well as its structure. The pusher assembly is designed for easy replacement in large detachable sections. Using heavy elements in the thrust canopy material presents a question. How can the additional mass of such a structure be rationalized when lower vehicle mass is one apparent goal of using nuclear fusion pulse propulsion? Consider that vehicles of a realistic scale will use a near-hemispherical sail design, as these engines will benefit from a maximum intersection with the blast. Forces produced by the fusion pellet's expanding shockwave of plasma are considerable, so even large additions of mass imposed by a hemisphere design is overshadowed by gains in efficiency from harnessing these forces. The entire hemisphere will need to withstand shock, tension, and compression in the direction of the detonation. The lightweight spinnaker sails possible on smaller vehicles are no longer practical at scale, especially considering larger sail area implies more frequent and extensive maintenance if made from lightweight materials. Conceding to a robust sail design made of aluminum trusses and cladding panels made of heavy elements will simplify the problem of eliminating waste heat as well. It provides ample area for either discrete radiators or passive cooling for the vehicle's laser amplifiers and nuclear power plants. A robust load-bearing hemispherical sail is further justified by the eventuality of fairly extensive maintenance on the vehicle. In our example, the Argonne will be expected to perform maintenance while on mission whenever not under thrust. This is accomplished by removal and replacement of sections of the sail, something made possible only by its manner of construction. While a thin sail material is lighter, it is more susceptible to debris impacts, also being arguably more difficult to repair. The sail would need to be carefully tensioned and patched, while adding mass would have to be avoided to maintain the sail's center of mass. The sail would need to be routinely inspected, repaired, and previous repairs constantly monitored for wear. Repairing a hard sail is a task requiring more movement of physical mass, but this task is less complex. Damage is of course more rare with this design, and when it does appear it will not pose an immediate risk in the same way a ripped sail might affect a ship's trajectory. The capability for a sail to be removed in modular sections not only simplifies maintenance, but offers interesting possibilities for alternative uses of the structure. These ideas were first posed in Project Orion and are adaptable to external fusion pulses as well. The use of transuranic elements in areas exposed to nuclear radiation accomplishes several functions. After extended normal operation, the pusher will be removed and used for nuclear reprocessing on distant bodies where nuclear material is difficult to source or transport. If the plate is rebuilt using more transuranic material, the vehicle can produce non-trivial amounts of useful nuclear material indefinitely. These elements not only block radiation, but can passively make use of this energy as they become more radioactive over time. One notable drawback is apparent, as materials are difficult to procure without industrial breeding of low-enriched nuclear material in space. It is often debated how linear pulling spinnakers can leverage a sail at the vehicle's bow, since the vehicle will be impacted by the reflecting blast wave and subsequently travel through the nuclear detonation's origin point. Interestingly, the advantage of a hemispherical versus a shallow concave sail design is to mitigate the reflection of the blast back towards the vehicle. The vast majority of the radiation from the pulse will arrive at the sail at a right angle to its surface in this design, increasing momentum transfer and also leaving reflected radiation bouncing back from the sail with considerably less energy. One potential effect of this will be the production of eddies in the plasma cloud as it converges, but this plasma will dissipate long before interaction with the main vehicle can occur. Both the sail's design and the brief effective lifetime of fast-moving plasma imply the actual losses in thrust resulting from deflection on the secondary blast wave as the vehicle passes through it are negligible. The rapid dissipation of the fusion reaction products mean only a basic radiation scattering shield is needed to protect the vehicle. While it is difficult to harness the phenomenon of nuclear fusion towards propulsion, vehicles designed around external fusion pulses are not necessarily complex engineering undertakings. Large-scale vehicles operating on pulsed inertial exchange can function upon simple principles and do not demand advanced manufacturing or materials. Material with high tensile strength and consistency, such as those needed for pressure vessels on chemical spacecraft, are largely avoided. Important assemblies, such as the crew module and power plants, could be fabricated elsewhere. These would be employed in the vehicle's construction as well, meaning such a vehicle might be built on entirely local materials after placing infrastructure assets in orbit. The Argonne was, to a limited extent, an example of one such emergent project. Its control module was originally the central module of the Tokhtar lunar station, which was relocated to the L3 Lagrange in order to be refit and serve as the main working area for the Argonne's crew. The third and fourth nuclear reactors were co-opted from lunar installations as well, one from the Tokhtar station and another from the Grimaldi surface base northeast of Mare Orientale Basin. Consider in legacy designs, including Dr. John Dale Solom's Medusa, each part of the vehicle is connected along a central truss and propulsive force is distributed through tension down the truss and across structural tethers connecting the spinnaker. The absence of compressive forces on the craft's hull structure is another contributor to the design's low manufacturing cost. We've mostly discussed very large vehicles here, in excess of 100,000 tons, for the application of pulsed nuclear fusion. This scale is viable because of the possibility of manufacture using in-situ resources from lunar orbit, but we don't necessarily need vehicles this large to fulfill the requirements of these systems. We can reason a useful system of classification from our discussions. For use in solar space, we can envision 3 tiers of fusion pulse spacecraft. The first tier represents proving or testing vehicles up to 5,000 tons. This is roughly twice the theoretical minimum mass for these vehicles, and thus it is a bare-bones estimate of a test platform. The second tier concerns all vehicles not intended for proof of function and less than 100,000 tons, possibly using a lightweight spinnaker-style sail. On the third and last tier, we have ships over 100,000 tons, making use of heavy structurally supported metal cladding. The minimal scale for these vehicles using today's technology we could expect to be around 500 to 1,000 tons, or roughly equivalent to 1 or 2 international space stations. This should permit carrying the nuclear reactors, lasers, and radiators needed. Such a vehicle at this minimal scale would act as a test platform, so the blast-absorbing canopy could be a flexible sail more akin to the spinnaker sail ships of Earth rather than a full or partial hemisphere. This means less of the blast will be intercepted for thrust, an acceptable compromise given the low cost of individual pulse devices. It might take years to a decade to build a 215,000-ton vehicle such as the Argonne exclusively in lunar orbit, depending on the intensity of efforts and the size of the ship, and assuming global cooperation. If construction is an endeavor made with near independence from Earth's industries, though, we can assume fabrication methods based on emergent technologies. These might include laser sintering of lunar aluminum dust into structural trusses, deposition printing, and other expedient techniques taking advantage of the space environment. Putting these vehicles into a specific context in our solar system presents another line of questions, mostly concerning operational hazards given distance to key regions for human activities around Terra, Luna, and the two bodies' Lagrange points. Electromagnetic pulses and electron activation represent the two main hazards. Since we are using fusion, radionuclide or fallout production is avoided. To properly argue the long-term effects on the space environment from operating a vehicle such as the Argonne, we will need to calculate the intensity of radiations as the craft crosses a normal flight trajectory. This is a technical problem outside the scope of this video, but we will return to this point in the future. This brings up another consideration. If we use high-performance systems on massive vehicles to transport raw material around the solar system, how will they interact with other industrial infrastructure? Employing networks of shuttles to offload vehicles laden with material, rather than parking them in local lunar orbits, might offer a way to reduce risk to surface operations on the Moon. The eventual design of interplanetary transportation networks will inform a more in-depth discussion of how pronounced the environmental interactions of these craft will be. The importance of any effect on the local space environment cannot be stressed enough, since this space will invariably be shared by human activity. The NPV Argonne carries at most 800 people. This is a not insignificant population whose needs have to be met. The comforts of daily life, including space for activity, resources, and food, must be satisfied as the vehicle makes infrequent stops across the solar system. We made the Argonne a base of operations for human activity on the outer planets in our premise, so that addressing human demands is a more straightforward question. We are assuming infrequent resupply stops and a large population, so our calculations are on the more extreme end. High redundancy and a multitude of services will be expected to ensure safety of the crew, in addition to basic needs with hundreds of days between resupply. These factors do imply the Argonne is expected to be somewhat self-sufficient, with routine or emergency resupply being a fairly inexpensive option as a backup. In this paradigm, if the Argonne intended to host a skeleton crew, her resource needs could be met entirely from the ship. During peak operation times, when the ship is fully manned, supplies could be shuttled in from wherever is convenient. Stepping back from the larger problems of sustaining the crew, we have to consider the immediate risk to the crew from operation of a nuclear fusion pulse drive. Orion offered a simple solution to the threat of radiation by placing a heavy metal pusher plate between the detonations and the crew. Using a spinnaker-style spindle design, as Argonne does, risks exposing the bulk of the spacecraft to its propulsion system's radiation. The main concerns to human biology and electronics are fast-moving helium nuclei, or alpha particles, and neutrons. Distance and shielding can reduce the danger of alpha particles to negligible levels, but the neutrons are not so easily defeated. Neutrons are most effectively countered by a combination of scatter shields and mass over distance. Scatter shields placed close to the neutron source deflect the neutrons, spreading their pattern and decreasing the total concentration of particles. The ship's mass, represented by payload, storage tanks, raw materials, and structural assemblies, are all placed between the detonation and the crew compartment to further scatter and shield against radiation. Thank you for watching. Subscribe to the channel for more content like this.